I just found another simulation on the web at the PHET website in Colorado that I think you might find very useful as far as the harmonic oscillator. So before we move on to our next topic, let me just show you that simulation, okay? So when you go to phet.colorado.edu, you can play with sims and find physics or chemistry. And then under physics, click on quantum phenomena. And this simulation right here, it says quantum bound states. That's a really nice simulation of the wave functions for harmonic oscillator. So let's click on that one. That's a Java applet. And then hit run now. It's going to download a Java applet to your computer, so you get a security warning. Just allow it to run on your computer. And this is what this simulation looks like. Now, in this particular simulation, it shows you the wave functions for a particle, okay, depending for different potentials. So you can have a square well, which we talked about before briefly when we immediately after we talked about tunneling. Down here, one of the options would be to pick a harmonic oscillator potential. So you can see, if you remember your harmonic oscillator potential, the potential energy is a quadratic, right? It's a parabola. So what you have here, shown here, is on this energy scale, you have the potential energy in purple. And then what did we say the allowed energies are of the harmonic oscillator? The allowed energies are E equals V plus a half times h nu. So the allowed energy levels are separated by each adjacent, and allowed energy levels are separated by h nu. So you can see these green lines right here, those are the allowed energy levels for your harmonic oscillator. So here I'm clicking here on that red line. What's that energy? That's the ground state, right? So for V equals 0, the energy is 0 plus 1/2 times h nu, so that's going to be equal to h nu. Shown below, I'm sorry? Yeah, 1/2 h nu. I'm sorry. Okay. Shown below, you have the probability density function. That's the square of the wave function. And you can see as time advances, that doesn't change. That's a stationary state. Okay? So what would happen if I were to plot the wave function itself? Okay. This is what the wave function looks like, and you can see it's changing. Okay? The wave function, what you're being shown here is the wave function is a function of time and coordinates. So your psi, if you remember, big psi is a function of coordinates times e to the negative I et over h bar, right? So it's going to be oscillating with time. The wave function itself, the total stationary state wave function will be oscillating with time. Okay, so here what you're looking at is just the real part, and then here's the imaginary part. So your imaginary part and the real part are both changing with time. But the magnitude itself of the wave function, if you just want the magnitude, that magnitude shown here as a white curve is constant, because that's just the square root of the square of the wave function. You have a stationary state. All right? And just to remind you, how do you get the real and imaginary components? Let me bring up the notebook right here. Oops, sorry. If you remember, okay, your big psi is equal to psi, which depends on x, times e to the minus I et over h bar, right? So that's the function of x times the function of time. This is just cosine et over h bar minus I sine et over h bar. So what you're saying is the real part is psi of x times cosine et over h bar So you can see this, the real part depends on time, okay? And the imaginary part is also dependent on time, psi of x times sine et over h bar. All right, so what you're seeing in your simulation is this part. This is the real part of big psi. Oops. Minus I times the imaginary part of big psi. Okay? And if you remember, because of this form right here, when you take the probability density function, you do psi star times psi. So if you do psi star times psi, complex conjugate of big psi times psi, that will just give you psi, little psi star times psi, because this term right here, the complex conjugate of that would just be e to the plus iet over h bar, and when you multiply that through, you just get e to the 0. So here's your probability density function. It's independent of time. You have a stationary state. Okay? And in that simulation, when it says magnitude, then magnitude of psi would just be the square root of psi star times psi. Okay? Which is the same thing as the square root of big psi star, big psi. So going back to that simulation. All right, so this is, you can see your magnitude is fixed, stationary state. Okay? Your real and imaginary components are changing with time. So down here you can see your time advancing. Now, when we solve for the Schrodinger, the time independent Schrodinger equation, if we're just solving for this little psi right here, what are we? And we're plotting that, then we're just assuming that time is 0, right? So when t is 0, that this term is going to be e to the 0. So if you pause this one, this time scale down here, and then just rewind back to time 0, what you're seeing there is the plot of little psi. Okay? So the magnitude there is just your little psi. Okay, so there's the magnitude. That's your little psi. Okay. And that's the real part. And then the imaginary part is 0. So your little psi is just a real function in this case. Okay. If you want the probability density, then you plot the square of psi, and that's what it looks like. All right. So that's for the ground state. You can see there's no node for v equals 0. What if you have v equals 1? Well, the first excited state, that's what you get. So for v equals 1, what do you have now? You have one node, right? And your energy E1 is going to be 1 plus 1/2 times h nu. So it's going to be 1.5 h nu. So here's for V1. Here's the probability density function. What would the wave function look like? It's going to look like that. So you have, so again, your imaginary part here is 0. Okay, this is the real part. And then the magnitude, if you just take the magnitude, you're just taking the absolute value of the real part. And that would be, let me see if I can make this look better. Okay, okay, so that's the, so this is the real part. You can see there's one node, right, at the origin. Okay, imaginary part is 0, so your entire function is real. And then the magnitude, that's just the absolute value of the real part. Okay? And then if you want to see how that evolves over time, you can hit this play button right here, and you can see how your overall wave function will be changing with time. And so you can see your real part and your imaginary part are changing. But if you look at your magnitude, your magnitude is fixed. Okay? Stationary state. That's why it's called a stationary state. We call it a stationary state not because the function, the wave function is independent of time, but because the probability density function is independent of time. It's the psi squared, or the magnitude of psi, that's independent of time for a stationary state. All right. What if you have v equals, let's pause this. Let's set it back to 0. Okay. So there's your wave function. For v equals 1, you can see there's one node, and this is an odd function. Okay? You can see it's an odd function. It's symmetric with respect to inversion through the origin. So if I have a point here, go to the origin, go a certain same distance to the other side, I'll hit the other side of the function. Okay. So psi of negative x would be equal to negative of psi of x. That's an odd function. What if you have v? Okay, go back to v equals 0. You'll notice your v equals 0 is symmetrical around the psi axis, the vertical axis. So you can see that that's an even function. And then for v equals 1, and then there's v equals 2. What do you notice about v equals 2? What did I just do? For v equals 2, what do you have? Oops. Again, you have an even function, and this time you have two nodes that are equidistant from the origin. Right? On either side of the origin, you have one node. So you have two nodes total. So number of nodes will just be equal to whatever the quantum number v is, because that's the degree of the polynomial in your expression for your wave function. What if v equals 3? This time you're going to have, again, you have an odd function, and you have, in addition to the node at the origin, you have another node on the left and another node on the right. So 3 nodes. Okay? So these nodes, these oscillations in between, is due to that polynomial term in your wave function. What's responsible for your wave function going to 0 at x infinity and x equals negative infinity? Your Gaussian, the Gaussian part of your, the exponential decay part of your wave function, e to the negative alpha x squared over 2. I think that's what it was, right? Okay, and we also talked about tunneling. And let me see if I can change the scale. I can't change the scale for the energy. But one thing you'll notice is this. If for v equals 0, the classical turning points are right here, right? And so we're saying that classically, if the energy of the particle corresponds to what the energy is for v equals 0, then your particle will be oscillating between these two distances, right? It's going to be oscillating between these two distances. These are your classical turning points right here, where all the energy is potential. Let's draw a vertical line down here. And what you'll notice is that there is a finite probability of finding the particle beyond the classical turning points. Okay? So according to classical mechanics, this is a classically forbidden region. This is a forbidden region. Oops. So this is classically forbidden. So, but there is a finite probability of finding the particle there. Okay. So, how would you calculate the probability of finding the particle in that classically forbidden region? You just integrate what? Integrate psi star psi dx from whatever that turning point is, the right turning point, to x equals infinity, right? That's the probability of finding the particle from here to infinity. And then it should be the same value you get from the negative turn by symmetry from the left turning point to negative infinity. So you just multiply that by 2. That would be the probability of finding the particle in the classically forbidden region. So this is a good simulation to look at, play with, if you want to familiarize yourself with the harmonic oscillator. Okay, so if you can go to higher wave functions, you can see you get more and more nodes as you get to higher V levels. This is side 13.